Hello and welcome to my video. Today we will find the locus of the local maximum point of the function fx defined as x cubed minus 3 times t plus 1x squared plus 12 times tx. And in case some of you haven't understood the problem, let me explain one more time. So this is a cubic function, therefore it can have a local maximum point. But here we have a changing parameter t, so if the value of t changes, the graph of the function also changes. We can easily observe this using the Desmos Graphing Calculator. So this is the graph of fx having changing parameter t. And if we change the value of t, you can clearly see that the graph changes, and therefore the local maximum point of the curve also changes. Now, if we change the value of t, it seems that this local maximum point moves on a certain curve. In other words, the collection of the local maximum points with different values of t constructs a certain curve, which is denoted as black dashed line here. This curve is called the locus, and we have to find the equation of this locus of the local maximum point. Alright, so now everyone must have understood what I'm going to accomplish here, but how can we find this locus? The general method of finding the locus on a coordinate plane is like this. First, let x, y be the local maximum point of fx. We use small x and y for the expression of our given function here. So let us use capital X and y specifically for the local maximum point here. The locus of the point capital X, capital Y means what shape or what curve does this point capital X, y draw? And this simply means the relation between capital X and capital Y, like y equals fx. So we have to find the relation between these two variables, x and y. Also another side note here, I use the notation capital X, y for the point on the locus because that's the notation that I'm most familiar with, but the notation really doesn't matter. You can use a, b, p, q, alpha, beta, or whatever you want. All we have to do is to find out the relation between two variables, and this relation is what matters. The notation matters not. Okay, now let's dive into our specific problem. In order to find the local maximum, we must first differentiate the function. So let's find out the derivative. So the derivative is given as 3x squared minus 6 times t plus 1x plus 12t. And we can take out 3 to the front, and we have x squared minus 2 times t plus 1x plus 4t. And this expression is further factorable. So if we do that, we have 3 times, and this part is x minus 2 times x minus 2t. So this is the derivative. So f prime x is actually a quadratic function, and the derivative becomes 0 and x equals 2 and x equals 2t. And if you know about the cubic function and its derivatives, you might already know that these are the point for local maximum and local minimum of the function. However, since t can have all real values, it is undetermined which one is greater between 2 or 2t. Therefore, depending on which is greater between 2 and 2t, there are 3 possible cases, and they are like this. So these are all 3 possible cases for the graph of f prime x, the derivative. Case 1 is when 2t is greater than 2, so t is greater than 1. The sign of the derivative is positive here, and negative here, and positive here. So the graph of y equals fx looks like this. And you can see that the local maximum occurs at x equals 2. Case 2 is when 2t is less than 2, so t is less than 1. In this case, the graph of fx looks similar, but now the local maximum occurs not at x equals 2, but at x equals 2t. Finally, case 3 is when 2 equals 2t, so t equals 1. In this case, the derivative simply becomes 3 times x minus 2 squared. So the derivative is non-negative for all x and only 0 at x equals 2. This means that fx never decreases and its slope becomes instantaneously 0 only at x equals 2. So therefore, in this case, fx does not have a local maximum point. So these are our three cases, and now let us find out the equation for the locus in each case. First, case 1. When t is greater than 1, 2t is greater than 2, and therefore the local maximum occurs at x equals 2. The local maximum value is f2, which is 8 minus 3 times 4 is 12, t plus 1 plus 12 times 2 is 24. So we have minus 4 plus 12t. Since we promised to indicate the local maximum point as capital X, capital Y, we can write capital X, the x coordinate of the local maximum point, is simply 2, and capital Y, y coordinate, is minus 4 plus 12t. So we have to find the relation between x and y. However, in this case, even when t changes, the x coordinate of the local maximum point is fixed to 2, and only y coordinates changes as t changes. From t being greater than 1, we obtain y is greater than 8. And therefore, we can simply write the locus as x equals 2 when y is greater than 8. And this is the locus when t is greater than 1. You can see that the local maximum point draws a vertical half line in this case. In case 2, where t is less than 1, now 2 is greater than 2t, and therefore the local maximum occurs at x equals 2t. So the local maximum value is f2t, and if you actually calculate f2t, you will obtain minus 4t cubed plus 12t square. And this is the local maximum point capital X, capital Y. So we have x coordinate as 2t and y coordinate as minus 4t cubed plus 12t square. Now both x and y contain the parameter t. In order to find the relation between x and y, we have to eliminate the parameter t. And we can do it like this. From here, t equals x over 2, and if we substitute this into here, we can eliminate t and obtain y equals minus 4 times now x over 2 cubed plus 12 times x over 2 square. So we obtain y equals minus x cubed over 2 plus 3x square. And note that from t being less than 1 and x equals 2t, we have the range of x being less than 2. And this is the locus when t is less than 1. The relation between x and y. Here, the local maximum point draws a cubic function. And in case 3, when t is equal to 1, I have already explained that fx does not have a local maximum. To summarize, the locus of x, y is the union of two parts obtained from cases 1 and 2, which is x equals 2 while y being greater than 8, and the cubic function y equals minus x cubed over 2 plus 3x squared when x being less than 2. And I have already said that the notation does not matter. If we want to draw this on small x, small y plane, we can simply change the variables into small x and small y. So we can say that the equation of the locus is this. If we draw this, we obtain this graph. This part, the vertical line, is for the case 1, where the equation of the locus is simply x equals 2. And this part, the cubic function locus, is for the case 2. Now, let us take a look at this point 2, 8. This point does not belong to either of two cases. Therefore, this point 2, 8 is excluded from the locus. So this was the plot of the locus. Right, so we have solved the problem and obtained the equation for the locus, and that's cool and all. But actually, let us go back to the Desmos Graphing Calculator again to more visually understand how the local maximum point moves on the locus as t changes. Let us start from case 1 where t is greater than 1. As we change the value of t in this range, you can see that the local maximum point indeed moves on the black solid vertical line, which is x equals 2, which is exactly the locus we obtained previously. Now let's take a look at case 2 where t is less than 1. Here, as you change the value of t, you can see that the local maximum point moves on black solid curve, which is the cubic function that we have obtained for the equation of the locus in this case. And finally, let us take a look at this point 2, 8, which was excluded from the locus. Note that the function passes this point when t is exactly 1, and that, my friend, is case 3. In that case, we have shown that fx does not have a local maximum point using its derivative. And you can see it from here that the curve does not have local maximum nor local minimum, and that's why this point 2, 8 must be excluded from the locus. Okay, so that was all for today's video. If you like this video, please hit that like button and also subscribe to my channel for more math videos. And I will see you in another video.